this video, we are going to be doing example 11.6, the seesaw. A father of mass MF and his daughter of mass MD sit on opposite ends of a seesaw at equal distances from the pivot at the center. The seesaw is modeled as a rigid rod of mass M and length L and is pivoted without friction. At a given moment, it rotates in a vertical plane with angular speed omega. A. Find an expression for the angular momentum of the system. B. Find an expression for the angular acceleration of the system when the seesaw makes an angle theta with the horizontal. So part A asks us to find an expression for the angular momentum. To do that, the first thing we need to do is find the moment of inertia of the system. So the problem tells us that the moment of inertia for the seesaw is going to be for a rigid rod. And if you look on page 304 in your textbook, the formula for the rod is ml squared over 12. Then the people on the seesaw we can model as particles. So the moment of inertia for each person is I equals mr squared. In this case, m will either be md for the for the daughter, or mf for the father. And in this case, r squared is r is L divided by 2. So the moment of inertia for each person is ml squared over 4. So the total moment of inertia is going to be the moment of inertia of the rod plus the moment of inertia of the father plus the moment of inertia of the daughter. If you find the least common denominator and combine it, you get this expression. Now, the next thing we have to do is just plug that into our formula for angular momentum. Remember, angular momentum equals I times omega. We already have our I, so we just multiply that by omega. And this right here is the answer to part A. Now, part B asks us to find the acceleration of the system when it makes an angle theta with the horizontal. So you can see that's what's pictured here. To do that, we need to find the net torque on the system, and we can use the equation net torque equals I times alpha. So, first, we have to realize that this angle here is also angle theta. And if you think about it in terms of trig and geometry, this angle here will be 90 minus theta. So this 90 minus theta, that is the angle that the force will make with the axis of rotation. That's the same angle right here as well. So if you recall, the torque, sorry, that's a really bad towel, is equal to FD sine, and instead of calling it theta, I'm going to call it phi. FD sine phi. So the force, let's talk about the father first. The force is the weight of the father pulling down. D is L over 2. And then the angle is going to be 90 minus theta. So remember that the sine of 90 minus theta sorry, this is so sloppy, is going to be equal to the cosine of theta. So we can change this to cosine theta right here. What this boils down to is that the torque caused by the father is equal to this. So the weight times the distance times the cosine of the theta. Oh, and sorry, you can, if you want to, you can factor out the L squared. Both of these answers are correct up here. For the torque caused by the daughter, it's going to be the same thing, except instead of MF, it's going to be MD. Now, the father is causing the system to rotate counterclockwise, and then the daughter would be causing the system to rotate clockwise. Remember, counterclockwise is the positive direction, so the torque is going to be the torque caused by the father minus the torque caused by the daughter. So the net torque is going to equal I times alpha. So for here, from this step to this step, I just plugged in the I that we got in part A of the problem. So in terms of algebra, what should you do next? Well, I would cancel out the L's. And I would also multiply everything by 12. Apparently I just copied and pasted that thing twice, so you can ignore this right here. Sorry about that. So if you cross out the L's and multiply by 12, you'll end up with this. Now what should we do? Remember, we're looking for the angular acceleration, so we want to divide both sides by this right here. And you should end up with this. And that is your final answer.